Hi, happy people. This is Mr. Wilcox. Video is for Algebra 2, and it's our lesson on solving inequalities. So last time we reviewed how to solve equations, which had equal signs. Today we're going to solve inequalities, which have different symbols. Just a reminder that you can pause the video at any time that you want to write down anything. So first thing, an inequality what is it? Well, if an equation uses an equal sign, an inequality uses one of these four symbols. So we have less than, greater than, less than or equal to, or greater than or equal to. The easiest way for me to remember the difference between less than and greater than, the less than kind of looks like the L for less than got squished and turned on its side. So L, less than. For the or equal to's, remember the difference between that is if we're looking for a number less than 2, you can't have 2. 2 is not less than 2. But if we want a number that's less than or equal to 2, then 2 can be in there because it is equal to. All right. So that little line underneath means equal to. And so one of these four symbols is going to be used in every one of our problems today. So before we actually get to solving a problem, we're going to define a variable inequality and learn how to graph it. So a one variable inequality has solutions that make the statement true. And for an equation, we usually had one answer that made it true. Sometimes we could have infinitely many solutions. But for inequalities, we're always going to have a lot of solutions. And that is why we're going to graph our solution, because it's going to be a part of a number line, a whole half of a number line. So to graph an inequality, what we're going to do is we're going to make a number line, and whatever number we are less than, greater than, less than or equal to, or greater than equal to, we're going to put on the number line, and we're going to put a dot there. So we're going to put an open dot if we have less than or greater than, and that open dot represents that that number is not part of our solution. And then when we have less than or equal to or greater than or equal to, we're going to put a closed dot signifying that that number is part of our solution. And then we're going to shade whichever direction of the number line makes those values make our inequality true. So the examples we're going to work with are x are greater than 4 and x is less than or equal to negative 3. So we're going to start with x is I don't like that color. Let's start with dark blue. There we go. X is greater than 4. So if x is greater than 4, we're going to put 4 in the middle. You should always have at least 5 numbers on your number line. All right. So if we have x is greater than 4, that means we're going to put in open dot at 4 because we are greater. You've got to be kidding me. All right. An open dot at 4. There we go. Because 4 cannot be part of our solution because 4 is not greater than 4. So we have to put an open dot there showing that 4 is not part of our solution. So now we could test a point. So is 5 greater than 4? Yes, it is. Is 6 greater than 4? It is. Is 3 greater than 4? It's not. So our answers that make our inequality true are on the right side here. So we are going to shade that direction. And we just shade it along the number line and then try to make a nice arrow. All right. So for x is less than or equal to negative 3, we're going to still have a number line, and we're still going to have at least 5 numbers. 1, 4, 5. All right. So at negative 3, we are going to put a closed dot because of that or equal to symbol that shows that negative 3 could be a solution. So if I put a negative 3 up above, it would work. So that is why I want a closed dot. So then again, we look on each side of the number line. Is negative 2 less than or equal to negative 3? It's not. Is -1? Nope. Is -4 less than or equal to -3? It is. Is -5 less than -3? Yup. So this time our answers that are making it true are to the left. So we're going to shade to the left and try to put in a nice arrow, right? So open dot for less than or greater than, close dot for less than or equal to or greater than or equal to, and then ask ourselves which side of the number line makes our statement true and shade in that direction. All right, one thing that is not only are the symbols different for inequalities, but the solving rules are slightly different for inequalities. So when we're solving using addition or subtraction, it's the same as equations. So you can add or subtract any number from an inequality and it stays the same. So we are going to use that rule to solve these two inequalities. I have 2 slides coming up, one for each, and then we are going to graph. So adding or subtracting a number doesn't change an inequality, so that's not different. But where we will see differences is when we multiply and divide. So our first example there was x minus 2 is less than or equal to 7. So to solve this inequality, we do it just like we would solve our equation. So we would add 2 to both sides. And remember, in Algebra 2, you don't have to show the step. I'm going to show it just so everyone can tell where it came from. So if I do that, I'm going to get x is less than or equal to, and 7 plus 2 is 9. Right? So I'm going to make a number line. I'm going to put 9 in the middle and make at least 5 points. 9, 10, and 11. All right, so because it's less than or equal to, I'm going to put a closed dot on 9, because if I put 9 in there, 9 is less than or equal to 9. It is equal to. So then we got to test each side of the equal sign. So is 8 less than or equal to 9? It is. Is 7? Yep. So it looks like our answers are going to the left. Let's just double check. Is 10 less than or equal to 9? No, it is not. It is bigger, not smaller. So here is our answer. So the values that make this inequality true are any number less than or equal to 9. And on a number line, that is represented by all the numbers smaller than 9 and not. All right, our second example was using subtraction. So if we have x plus 6 is greater than -1, the inverse operation of adding 6 is subtracting 6. So if we subtract 6 from both sides, we get x is greater than -7. And if x is greater than -7, we're going to make a number line. And we're going to put -7 in the middle. Oh, maybe that doesn't look like -7. All right. There we go. 6, -5, 8, -9. All right. So we're going to put an open dot on -7, because if I put in -7, -7 is not greater than -7, so it's not part of our solution. Now we're going to test a point on each side. So is -8 greater than -7? It is not. It is smaller. Is -5 bigger than -7? It is. So our answers that make this true must lie to the right. So we're going to shade that side. Try to put a arrow on it. And this is our answer. All right. All right. So I told you that adding and subtracting are the same, but the rules change a little when we multiply or divide. So when we multiply or divide, if we multiply or divide both sides by a positive number, then our inequality doesn't change. It's just like solving an equation. But if we multiply or divide both sides by a negative number, in order to keep our solution true, we have to flip the inequality symbol. So less thans become greater thans and vice versa. So here's the 2 examples we're going to work with. And again, I have more slides so we can do that. So again, adding or multiplying or dividing by a positive number, we're going to keep the symbol the same. Multiply and divide both sides by a negative number, we're going to flip the symbol. So our first example is negative is y to, wait, what? Is negative 2x is less than 18. So in order to solve this problem, we're going to divide both sides by negative 2. And since I divided both sides by a negative number, I now have to flip this symbol in order to make it true. So I'm going to get x is greater than negative 9. So the reason I had to flip that is because if we look at our number line down here, and if I plugged in, I'm going to put in an open dot for negative 9, and then we're going to look for numbers that are bigger, so negative 8. If I plugged in negative 8 up here, 2 times negative 8 is 16, and 16 is less than 18, so that makes it true. And if I put in negative 10, negative 2 times negative 10 is 20. 20 is not less than 18, so that makes it false. If I had not flipped this symbol, then we would have still had a less than symbol, and I would have actually shaded to the left and chose numbers that do not make this true. But because I flipped this symbol, because I divide by a negative number, the numbers that are actually bigger and make this statement true when we plug it back into the original one are going to be shaded, and that's what we want. We want numbers that make our inequality true. All right, so here is our answer for that. All right, our second example is y divided by 4 is greater than or equal to 5. So if we're dividing by 4, the inverse operation is to multiply by 4. So I'm going to multiply by 4 on each side. So if I do that, my 4's cancel out. I'm left with y and 20. And because I multiplied both sides by a positive number, I'm going to keep the symbol the same. Because when we draw our number line and we put 20 in the middle and we put 21, 22, 18, and 19. So when we look at our numbers, 20 needs to have a closed dot because we have an or equals to. And is 19 bigger than 20? No, it's not. Is 21 bigger than 20? Yes, it is. So we're going in 22. So if I put in 24, 24 divided by 4 is 6. 6 is greater than 5. So 24 is on this side. So that is why we keep it the same, because if we flipped it now, it would make it untrue. So here is our answer. We multiplied by a positive number. We kept the symbol the same. We got an answer, and we graphed. So I just have more examples for you. So if we're going to just step it up and add more steps. So if I was to solve 4x plus 9 is less than 25, the inverse operation of adding 9 is subtracting 9. So I'm going to subtract 9 from both sides. So I'll get 4x is less than, and 25 minus 9 is 16. And if I divide each side by 4, I'm dividing by a positive number, so I'm going to keep my symbol the same. So I'll get x is less than 4. And then when I graph my answer, since we have a less than, I'm going to put a open dot. Is 2 less than 4? Yes, it is. Is 6 less than 4? No, it's not. So it looks like I'm going to shade to the left. And again, try to put a nice arrow on there. All right, so here is our inequality answer. All right, next example. We have 1 minus 3x is greater than or equal to negative 14. So the inverse of having a positive 1 is subtracting 1. So if I subtract 1 from each side, I get negative 3x is greater than or equal to, and negative 14 minus 1 is negative 15. Notice I didn't flip the symbol because I subtracted. I did not divide by a negative 1. I subtracted by a negative 1. So then I'm going to divide each side. And if I do that, I'm going to divide by -3. And notice I divided both sides by a negative number. So to keep our statement true, when I simplify on this side, I'm going to get x. When I simplify on this side, I'm going to get 5. And I have to flip the symbol to keep it true. So we want numbers that are less than or equal to 5. So I'm going to put 5 in the middle, 6 and 7, 4, 3. So I'm going to put a close dot on 5 because I can plug in 5 here and get a true statement and check each side. Is 4 less than or equal to 5? It is. Is 6 less than or equal to 5? It is not. So again, it looks like we're shading to the left. And so we want numbers that are smaller than or equal to 5. So that's all the numbers in the left-hand direction. All right. All right, I have one last example for you, and then we are done. So I have 3 minus x is greater than x minus 9. So both sides are simplified, but I have a variable on each side. So I can either add this x over or subtract this x over. So what I'm going to do is I'm going to add x to both sides because I want these ones to cancel out. So I'll be left with 3. And I added x, so that I'll get a positive number in front of my x. So 1x plus 1x is 2x minus 9. So now I'm just going to add 9 to both sides. So I'll get 12 is greater than x. There's 2x. And then if I divide by 2, I get 6 is greater than x. So if I get 6 is greater than x, I'm going to make a number line. 6, 7, and 8. 5 and 4. So I have 6 is greater than x as my solution. So I'm going to put an open dot because it's greater than. Because if I put 6 in here, 6 is not greater than 6. So I'm going to test each side. Is 6 greater than 4? No, it's not. Or yes, it is. Sorry, 6 is greater than 4. Is 6 greater than 8? No, it's not. So it looks like we're looking at numbers to the left. Now, if it bothers you, you can absolutely switch this so that this says x is less than 6, but 6 is greater than x is fine as well. All right, so that's it. This homework assignment is on Brightspace for you, as long as pictures of the page. Remember, you're just solving inequalities by using your steps to solve equations, except if you divide or multiply both sides by a negative number. Got to flip the symbol, and you have to graph your solutions. All right, so have a great day, Cardinals, and make it count.